Hello, Chemistry 1 students. Here are your Chapter 5 notes. It's day 4 of your notes, and we will be covering the portion of your outline that starts with isotopes, and we will go through and finish the atomic mass of an element. So at this time, you should get your outline out and in front of you. You may also find it helpful to have a periodic table as well. Remember, if you don't have a periodic table anywhere else, the inside back cover of your textbook does have a periodic table you may use. So, we're going to begin by talking about isotopes, and specifically, what is an isotope? So, the definition of an isotope, okay? The definition of an isotope is atoms that have the same number of protons. Now, while you kind of catch up on writing that, I want you to think about why it is that these atoms have to have the same number of protons. But a different number of neutrons. So part of what that means is that all isotopes have the same number of protons and electrons, but a different number of neutrons. So, kind of let's go back up to my first question about why is it that isotopes have to have the same number of protons, or what does that mean about an isotope? Well, remember, the same number of protons, remember we talked about the fact that atomic number, which is the number of protons, is what identifies an atom. So what that means is, if isotopes have the same numbers of protons, then they must be all the same atom. Okay, so when we start to talk about isotopes here, we're going to discover that an element can have several different isotopes. They're all the same element, they're all the same atom, but they have different numbers of neutrons. Now, looking at this kind of second part about the fact that all isotopes have the same number of protons and electrons, but a different number of neutrons, what does the fact that this atom, these different atoms, have the same number of protons and electrons? Remember, protons are positively charged, electrons are negatively charged, so I have an equal number of positively charged protons and negatively charged electrons. Right? What that is saying here is that all isotopes are neutral atoms. They don't have a charge. They don't have a charge because we have an equal number of positively charged protons and negatively charged electrons. So again, you kind of want to write a couple little why, if you will, explanations about that underlined information. If you need a little time to get that down in your notes, you certainly could pause your notes. Or pause the video, sorry. So because, and this is kind of a standard abbreviation for because isotopes of an element. Remember, we talked the other day about the fact that you can really kind of use the term element and atom interchangeably. The only difference between them is how many you're talking about. By definition, an element is a whole bunch of the same atoms together. Whereas if you talk about an atom, you could be talking about one single atom. So because the isotopes of an element have different numbers of neutrons, right? Because that's what we kind of reiterated here a couple times, right? We notice we have different numbers of neutrons as the definition. All isotopes have different numbers of neutrons, right? So that's important, obviously, to isotopes. So because the isotopes of an element have different numbers of neutrons, they also have different mass numbers. Because again, we talked about this just the other day, right? That the mass number is equal to the number of protons plus the number of neutrons. So all of these atoms that are isotopes, their number of protons stays the same. But we're saying here that we have different numbers of neutrons, which also means that their mass numbers are going to be different. So kind of that why do they have different mass numbers? So again, you would want to kind of explain that, okay? That's because mass number is the total number of protons and neutrons. Although all of these atoms have, these different isotopes have the same number of protons, because they're going to have different numbers of neutrons, that also means that their mass numbers will be different. Isotopes are fairly important to chemists because they are chemically alike, meaning that they react in chemical reactions the same way. And that's because they have identical numbers of protons and electrons. Most all the chemical behavior is because of electrons in atoms. So the fact that isotopes have the same number of electrons, and because they have the same number of protons, which means they're the same atom, these isotopes, although they have different mass numbers, tend to react the same way in chemical reactions. Isotopes, okay. Keep in mind that the number of neutrons in isotopes of the elements doesn't change the element it is because its atomic number, which remember is the number of protons, doesn't change. And every element on the periodic table has its own atomic number. So if my atomic number of the atom doesn't change, then it has to still be the same atom. So we're going to take a look at an example here. These are going to be 3 isotopes of neon. Neon 20, neon 21, and neon 22. Now, again, this is kind of going back to that shorthand notation and those different ways you can represent information. Remember from the other day, mass numbers are not on the periodic table. So somehow you have to be given the mass number. Remember, in all 3 of these are our mass numbers. Again, when we give a name with a hyphen and a number behind it, this is always our mass number. When we use an element symbol with a hyphen, that's also a mass number. And remember, in this 3rd notation, our mass numbers are top number. Now, I didn't put the atomic number here. You could, but remember, you don't need the atomic number because you have a periodic table. And using your periodic table and finding the element symbol Ne, which is neon, you can find its atomic number. Remember, you can know which number is the atomic number because it's a whole number, and it's going to change by 1 for each element on the periodic table because it's how the periodic table is organized. So, these are examples of some isotopes. If you would please figure out how many protons, how many electrons, and how many neutrons each of these isotopes has. I'll give you a moment to do that. You might already have done it while I was talking. So again, when you look up neon on the periodic table, you find its atomic number is 10, which means it has 10 protons because the atomic number tells me the number of protons. Because isotopes do not have a charge, they have to also have 10 electrons so that they have the same number of positively charged protons as they do negatively charged electrons. So, how do I figure out the number of neutrons? Remember, that is my mass number minus my number of protons, which for neon 20 is 10. So now if I take a look at neon 21, the isotope neon 21, I'm still going to have 10 protons because it's still neon and it still has an atomic number of 10. I'm still going to have 10 electrons because it's still a neutral atom, and so I still have to have the same number, an equal number of protons and electrons to one another. When I come to my neutrons this time though, my mass number is 21 and I'm subtracting 10, so I end up with 11 neutrons. Our last isotope of neon is neon 22. Again, neon 22 has 10 protons because neon's atomic number is 10. Neon 22 has 10 electrons because it's a neutral atom, so the number of positively charged protons has to be the same as the number of negatively charged electrons. Lastly, my number of neutrons in this case is going to be 12 because I'm going to take my mass number of 22 and subtract my atomic number, which is 10. So notice if we kind of go back to our definition of isotopes, isotopes are atoms that have the same number of protons but different numbers of neutrons, which means they have different mass numbers, and we just saw evidence of that. We have 3 isotopes here, all of which have the same atomic number and therefore the same number of protons. But what's different about them is that they have different numbers of neutrons, right? They have different numbers of neutrons, and as a result, they have different mass numbers. So we kind of just looked at 3 isotopes and saw that our definition of isotopes is indeed true. So why are isotopes so important? Well, they do have some usefulness. For example, many of you have probably heard about carbon-14 dating, probably in biology class when you've talked about how they know how old fossils are. So carbon-14 dating is called radiometric dating. And it's based on 2 facts. Fact number 1 is that each element exists as more than one isotope. And the second fact is that some isotopes undergo radioactive decay and the reason they do this is because they have an unstable ratio of protons to neutrons. So this is why, or these are kind of the ideas that allow any kind of radiometric dating, and specifically carbon-14 dating, to work. So that means that we have what's called a half-life of an isotope, which is the amount of time it takes for half the atoms of the sample of a particular isotope to decay. What we mean by decay is kind of what you really think of as decay, which just means really break down. Okay? So these isotopes that are unstable, because they have that unstable ratio of protons and neutrons, they break down. Okay? And for carbon-14, the half-life equals 5,730 years. Now, this isn't the only use of isotopes. If you have heard of someone who is getting radiation treatment oftentimes for cancer, right? They're using radio, and they typically, as well as chemotherapy, they're often giving the patient a dose of something that is kind of radioactive. And it specifically attacks the cancer cells that are bad and that you want to kill. And it decays and it releases radiation right at the site of those cancer cells. And so it delivers and kind of targets these fast-growing cancer cells and destroys them. Now, that's also, though, part of the reason why oftentimes people undergoing these treatments lose their hair. Because besides cancer cells that are fast growing, the other cells in your body that oftentimes are fast growing are your hair follicles and your hair. And so oftentimes, unfortunately, these chemicals, they also attack the hair follicles. So that's why oftentimes people lose their hair during chemotherapy and radiation treatments. And again, on page 127 in your textbook, there's a nice little easy to read article about carbon-14 dating and explaining in more detail about how things work. So I'd really encourage you to take the time to read that in your textbook. All right, so because atoms exist as different isotopes, that makes finding the mass of an atom a little bit more complicated. Okay, so we're going to talk about atomic mass. So what we're talking about is, where do those big long numbers, the decimal numbers for the elements on the periodic table that most periodic tables call atomic weight, where do those numbers come from? And that's what we're going to talk about, is where do those numbers come from? What do they represent? So as we start to talk about atomic mass, keep in mind again that the mass of even the largest atom is incredibly small. Because remember, we can't see atoms. They're too small. Can't even see them with our microscopes in biology class. We need a special scanning electron microscope to see them. However, it is possible to determine these atomic masses. So you can determine these tiny masses using a mass spectrometer. Now, this is actually a device that if you take a college chemistry class, specifically if you take organic chemistry, which is typically the second year of college chemistry classes, this is probably an instrument you'll use. It's not an instrument we have at the high school level, but it is a common instrument at the college level for college students to use. To give you an example of kind of how small we're talking about, the atom fluorine has a mass of 3.155 times 10 to the negative 23rd grams. The element arsenic has a mass of 1.244 times 10 to the negative 22nd grams. So these are tiny, tiny masses. And one thing about chemists is, although there's some math and such in chemistry, in general, chemists are not overly fond of math and of complicated math. So although these masses are useful to know, they are inconveniently small and impractical to work with. So scientists really, chemists in particular, really don't want to work with these tiny little numbers, okay? So as a result of that, chemists thought about it and they tried to come up with a way that they weren't dealing with tiny little numbers, okay? So chemists found that it was more useful to compare relative masses of the atoms using a reference isotope as a standard. So what we mean by relative masses is chemists are going to choose an atom and they're going to say this atom has a mass of this amount. And then they're going to compare every other atom on the periodic table to the mass of that atom. Okay? So, the reference that was chosen, okay, or the standard, or reference isotope, to be carbon 12. Now, that's not a little quinky dink. Chemists actually very specifically and purposefully chose carbon 12. And we're going to talk about that in just a couple minutes. And this carbon 12 was assigned a mass of exactly 12 atomic mass units. So, what is an atomic mass unit? An atomic mass unit is defined as an atomic mass unit is defined as 1/12 of the mass of a carbon 12 atom. Now, again, like I told you, chemists didn't just choose this randomly. Chemists purposefully chose carbon 12 because of the structure of carbon 12. So keep in mind that carbon 12 is going to have 6 protons because its atomic number is 6. And because it has 6 protons and the mass number is 12, it also has 6 neutrons. And a mass equal to 12 atomic mass units. Therefore, okay, 1 proton equals the mass of 1/12 carbon 12, or 1 AMU. Which, remember when we talked about protons and neutrons, we said that they basically have the same mass. So, by choosing carbon 12 purposefully, the result is that a proton equals 1 atomic mass unit in terms of mass, and a neutron equals 1 atomic mass unit in terms of mass. Okay, so this was done purposefully so that a proton or a neutron has an atomic mass unit, an atomic mass of 1. In nature, most elements occur as a mixture of two or more isotopes. Now, scientists do know something about these isotopes. So scientists and chemists know that each isotope has a fixed mass. So all we mean by fixed is that it's constant, it doesn't change. And a natural percent abundance. All that means is we know what percentage of the overall total atoms are this particular isotope. So, for example, looking at hydrogen, hydrogen 1 is 99.985% of the hydrogen that exists in nature. So you'll notice that the atomic mass on the periodic table for hydrogen is equal to 1.0079 AMUs. So all those numbers on your periodic table, the units for them would be atomic mass units. Now, the reason that this is not 1, okay, so the reason that this atomic mass of hydrogen isn't just 1 AMU, okay, so it's not 1 AMU because it takes into account the larger mass but smaller amounts of the other two isotopes of hydrogen. And that's why all of those elements on the periodic table have big, long decimal numbers for their atomic weight or their atomic mass. Because all of those masses are taking into consideration all of the different naturally occurring isotopes. So, how do we get those numbers? Those numbers are a weighted average mass of the atoms in a naturally occurring sample of the element. So for hydrogen, that takes into account the 99.985% hydrogen 1, but also the smaller percentages of hydrogen 2 and hydrogen 3 that exist in nature. So again, these atomic masses, okay, they reflect both the mass and relative abundance of the isotopes as they occur in nature. So, how do you actually calculate it? Because you are going to need to be able to use a calculator and calculate these. So, to calculate, you must know three things. The number of stable isotopes, of the element, the mass of each isotope, and the natural percent abundance of each isotope. So three things you have to know to be able to calculate these. First off, how many different isotopes there are that are stable, what the mass of each of those isotopes is, and then what is their natural percent abundance. To actually do this, so to do the calculation, the atomic mass of an element, you're going to multiply the mass of each isotope by its natural abundance. Expressed as a decimal. And then add the products. So here's an equation. Your average atomic mass equals the percent as a decimal times the mass plus the percent as a decimal times the mass plus the percent as a decimal times the mass, and I'm just going to write plus, etc. So if the element is like hydrogen that only has 3 isotopes, I would just do this 3 times. If I happen to do an element that has 5 isotopes naturally occurring, I would have to do this over 5 times. So this is how you calculate that average atomic mass. And, you did that last week on that ChemQuest 14. Okay, so you kind of did a little bit of this already when you did that ChemQuest. So we want to take a look at an example. For example, we're going to look at the fact that we have carbon 12, which is 98.89%, and has a mass of 12.000 AMUs. And then there's also carbon-13, which is 1.11% and has a mass of 13.003 AMUs. Now notice we didn't talk about carbon-14. That's because it's not a naturally occurring isotope. So to calculate our average for carbon, we're going to take our first percentage as a decimal, and remember, to change a percentage to a decimal, we just move our decimal places 2 places to the left. So it's 0.9889 times 12.000 AMUs plus, because we have 2 isotopes, we have to do this again, 0.0111, because again, I have to move my decimal twice, times 13.003 AMUs. So when you put that in your calculator, you should get an answer. Now we're going to use the same number of decimal places for our average as what they give us in the problem. So in this case, they gave us 3. So your calculator should give you about 12.011. And then the units are atomic mass units, or AMUs. And in science, you always need to have units on numbers, because otherwise the number really doesn't make sense. So this is why, okay, these atomic weights or atomic masses are not whole numbers on the periodic table. Because again, those numbers have taken into account all the different naturally occurring isotopes of that element, what their percentage is, what the mass is, and calculated that atomic weight. And again, showed you an example of how to do that for carbon. So that brings us to a good spot to stop. Taking a look at your homework assignment, remember I'd like you to set up your homework so that the top of your paper kind of looks like this. Okay, so I want the top of your paper to have this information. Somewhere at the top of your paper, I want your first and last name, the date, what class period you're in. Somewhere at the top of your paper, I want the homework. I'm going to number all the homework. It just makes it a little bit easier to keep track of them. But I don't want just the homework number on the top of your paper. I always want your paper to also reference what the assignment is. In this case, your assignment is from page 121 in your textbook. You're going to answer questions 18 through 21, and then also question number 23. You have 2 choices of how you want to do this. Okay, choice number 1, you can type this up using Google Docs. Okay, it's not necessary to answer these in complete sentences, although you're welcome to do so if you would like to. Your second choice for how you choose to do this is that you may handwrite this on a piece of paper, but then you're going to have to take a readable photo of your paper and upload that photo to your Google Drive. Now, that's pretty easy to do if you have a smartphone and you have your Google Drive. There's an app for your Google Drive on your phone that you can get for your phone. And if you have that app, then you can just go into that app and make sure if you have a personal Gmail account that you're logged in with your school one on your phone. And then you can do there's a little plus that comes up, and you can click on that and say upload, and your picture will show up then after you upload it in your Google Drive. Either way you choose to do it, when you are done with your homework, okay, you must submit, okay, either the Google Doc or the picture for the assignment in Google Classroom, which means you have to click on the assignment, you have to view the assignment, and then up in the upper right hand corner there's a like plus sign, so you're going to click on that plus and you're going to choose something from your Google Drive and you're going to attach it, and then you have to click submit. That happens a lot. You've got to remember to click submit at the end after you've attached your file. Now, if you're doing something in Google Docs, I do request that you title your doc as your last name and then the homework number. So, for example, if I was doing this homework and typing it up in Google Doc, I would call it Kremschreider and then homework number 2, all as the file name for the homework assignment. So again, your choice depending upon what your preference is, but either which way, you're going to submit it. You have to attach it in the assignment and submit it. And again, there is a DVD or a video that I made that's on your general class resources that talks about how to navigate. There's a material that has how to navigate Google Classroom, and there's a video I made there showing you this process. So I hope you have a great day. I will see you or talk to you tomorrow.